Hi everyone, my name is Ben Walker. I am a technical lead for SPDK, and today I'm going to be doing a talk on TCP networking for storage software developers. And we're going to cover mostly basics and intro today in the time we have. Hopefully this gets everybody up to speed sort of to where SPDK is at live right now. And then if anybody's interested to go further on our current research and development projects, they would be ramped up to do so. So let's get right into it. Some notices and disclaimers, and then a little bit of an outline. So we'll start with some level setting, which I'm going to go through pretty quickly. Probably too fast if you're actually not already familiar with this, but it'll at least give an overview of sort of the current state of the art for most software projects. Then we're going to get into some of the extra stuff that SPDK has already done and has done for a number of years, extra features like zero copy and clever batching and things like that. And then we'll spend just a little bit of time on the future, the current active work. But if you are interested in a lot more discussion on that, you can always find us on Slack. So first, what makes networking storage networking? I think is a great question. And for me, for storage networking, there's always some sort of fixed size queue or ring being modeled over the TCP stream. There's a limited number of slots in this ring that you can send messages in, and it's sort of flow controlled that way. All of the packets that we typically see, or all of the networking operations we typically see, are this sort of a blender, as I have there, of small and large packets. So the data is always a multiple of 4K, a block, but the commands are small and they're all interleaved on the same stream. So we have this mix of small packets and large packets. And then probably most importantly is storage networking has long-lived connections. The connections don't come up, send some messages, and go away. They stay there for a long time. Okay, so we'll go into the sort of the basics and the level setting first, and I'll whip through this pretty quickly. But every operating system we'll discuss today represents a connection as a socket. This API is actually from 1983. It's been very successful. Everybody's used it. There are some OS-specific extensions and some behavioral differences, particularly between Windows and the others. These are not gigantic differences. Usually things work pretty similarly, except for the mechanisms for grouping sockets. So the basics are data is sent using the send system call, and data is received using the receive system call. And these, by default, are typically blocking operations. Send tries to sit in the kernel until it can copy your data into the operating system buffer, so the operating system has a copy of it, just in case it needs to retransmit, and then it returns. And the receive side similarly waits until at least 1 byte, or the low watermark number of bytes, has arrived before the call returns. So if you were to sit down and say, hey, I know about the send and receive system calls and what a socket is, I'm going to write a simple server. And I want the server to scale across CPU cores and be able to support multiple connections. How would you do this in the most naive way? Well, the starting point is probably to have one thread accepting new connections, and for every new socket that's created out of that, spawn a thread, and have that thread sit and receive, doing a blocking receive, and send responses with a blocking send. This is like the old Apache HTTPD model, the old web server from late 90s. That's how it originally worked. And the code is actually very clean and relatively simple and robust. The problem is it doesn't perform very well. This is because if you have too many connections, you end up with a lot of threads, and you're swapping threads back and forth, and that's very expensive. this is still just a fine model if you have a relatively small number of connections and you're doing something really simple. Okay, so to make this better, we need to reduce the total number of threads in the system without having to reduce the number of connections we're handling. So we need to handle more than one socket per thread, basically. Uh, Ideally, we would have one thread per core. Sounds familiar, like SPDK. That's typically how optimal server designs work. Um, and we would eliminate thread swapping overhead entirely, and we would just multiplex a bunch of sockets onto that set of one thread per core. So this is notably how Nginx works. Actually, Nginx is completely single-threaded, and you just spawn multiple Nginxs, but same idea. And to do this, we're going to need some way to make the send and receive operations not block. And that's because if we try to do receive on one of the sockets of the set that our thread is supposed to be working on, it's going to sit there and block until it receives something. And what if it doesn't on that particular socket? What if the other ones are busy and waiting and nothing happens on the one we are blocking on? So we've got to, at a minimum, make our operations not block so that we can just move on to one of the other connections in our current set. And then we're going to need some efficient way to group the connections together so that we're not just sitting in a loop over our set of sockets, calling send and receive as fast as we can. So a little bit about blocking versus non-blocking. Sockets can be switched globally into non-blocking mode. This is what SPDK does. They can also be created in non-blocking mode, at least on Linux and FreeBSD. And individual send and receive calls actually have flags where you can control the blocking or non-blocking behavior that will supersede the global behavior on the socket. SPDK is doing everything non-blocking all the time for every call. So let's say we just discovered non-blocking capabilities, and we go modify our previous web server that we described. We're going to spawn one thread per core. On each thread, we're going to loop over our set of sockets that we're supposed to be handling, and we're going to perform non-blocking send and receive calls. We're going to attempt to receive, see if we got anything, attempt to send our response, and if we can't, we'll try again on the next loop. And this is great. We have no more context switches from threads. There's one thread per core. That's all fantastic, except now we're making system calls very, very fast, over and over and over again, all the time, and that is going to really hurt. So the way out of this is a simple observation. It's that as the number of sockets in the system goes up, the number of connections goes up, your bandwidth is fixed that your hardware can do. So necessarily, most of your connections, most of your sockets at any given point in time are idle. So we're going to use that for the next step. And that's about grouping the connections in a better way than just a list. So the original Berkeley Sockets API has a mechanism for reducing the number of system calls. It's the poll system call. And you can basically pass it an array of pollFD objects. And it will go check all of the sockets in that array, and it will report back to you which ones are ready to send or receive. And so we can just build up that set, call one system call, and it will tell us all the ones that are ready, and we can, only for the ones that are ready, attempt to do non-blocking sends and receives. And we can stop doing speculative receives on every socket in the set on every loop. And so we reduce the system call overhead by a lot with this. It is significantly better than the previous, but note that the kernel internally is still just doing a list over the set and attempting it. So you're not making a system call for every single one, but it's still iterating inside the kernel. So if you scale up to thousands of sockets or something, it's still not particularly efficient. Fortunately, there are better mechanisms for grouping on both Linux and FreeBSD. There On Linux, it's epoll, which I'm sure everybody is familiar with, and on FreeBSD, it's KQ, which I'm not going to talk a lot about. It's more or less like epoll. There are some key differences that some people think make KQ superior, but for our purposes, we can mostly treat them as conceptually the same thing. But the idea is that you create a set of sockets in the kernel up front, and you can add or remove sockets from that set. So the kernel now has like this internal object that is the set of sockets that is supposed to be checking on. Then when a network event happens, like an interrupt from the NIC or something happens, the kernel marks the socket in the set as ready, as data is ready, or it's ready to send again, or whatever it is. And this operation is O1. Instead of iterating through all the sockets, it's just saying, oh, I got an interrupt for this, this connection. I appended things to the TCP stream that it's waiting, it's got buffered up in the kernel. I'm going to mark that socket saying, hey, next time you poll, this one's ready. And then when the user later checks via epoll wait which set of sockets are ready, have data that's ready to be received, or have cleared out their send buffers and are ready to send again, then epoll will just return the set that it's already built internally based on the network events, the hardware events. And so it doesn't have to iterate over the set of connections anymore. That's much more efficient. So if we update our design again one more time, we will spawn one thread per core. On each thread, we will create an epoll or a KQ object, and then we will loop over that, loop around asking the epoll or KQ object on each iteration which sockets have data or which sockets are ready to send if we're trying to send data. And it will tell us which ones, and then we call receive on that set. So this is much better. There's no more iterating over the set. And this sort of design that we've finally gotten to here, after going very quickly through the level setting phase, is considered state of the art by most software applications. This is really how things work typically. And this is what SPDK mostly does today. Okay, so let's talk about the interesting stuff, the stuff that's not sort of how to write a server 101 level things. Let's get into the more nuanced and advanced topics here. So we have a server with some number of threads, one per core, and we've got a one of the threads is periodically attempting to accept new connections. How should we assign those connections to the threads? How do we distribute them? The most obvious way is just round robin, spread them out. But of course, the activity level of the sockets changes over time. And so simple round robin may result in some of the connections may be very active and some idle. And so you could end up with all of the active ones on one core, and you're not processing things effectively. So, some people may think, oh, we could distribute based on activity, which a lot of things try to do. We have not found that to be particularly effective because the activity level is very spiky. And so by the time we can react to too much grouping of active connections on one thread and shuffle things around, the profile has changed. So we have not generally found that to be a major improvement. It doesn't seem to be worth it. But we have found another way, which is, should we consider what's most efficient for the hardware, for the NIC? And so let's think about that for a minute. Packets arrive on the NIC from into an RX queue, and usually the NICs, they work kind of like a storage device for people who are familiar here, where they have queues, and they usually make one of these RX queues per core, not always, but commonly, much like we do one NVMe queue per core. And the NIC hardware itself will take a look at the packet headers often, and it will decide which RxQ to dump incoming Ethernet frames into. And it has a couple of ways to do this. It can just do it pure round robin, just distribute them all. It can do it based on the, with a couple different algorithms based on the four tuple being, the two IP addresses on either side of the connection and the two ports. And that tends to keep all of the packets for one connection, in any given connection, on one RxQ. And that's generally the most common way. It's most cache friendly. But let's think about what happens here. SPDK or software like it may select a thread that's running on core 1, and that's where we're going to do all the processing for that connection going forward. But the NIC algorithm, the hardware algorithm inside of the NIC, may have selected the RxQ associated with core 0. And so this means that all of the packets are arriving on core 0, and then they have to get passed over to core 1 using a lock or some kind of message passing system whenever core 1 calls receive. And actually, this is a major performance problem. It causes a lot of issues, especially jitter, P99 latency, because we need our threads, kernel tasks to wake up at the right time and get things shuffled over, or we're waiting on a lock or something like that. So what actually might be the best question to ask as we're distributing our sockets to the groups is, can we align these to the RxQs? And the answer is yes, we can. So there are relatively new hints that tell you which RxQs are associated with which sockets, or really which sockets are associated with which RxQs. And there's a couple different ways this can happen. There's two flags. You can do get sock opt to get on the you can ask the socket using either SO incoming CPU or SO incoming NAPI ID, and it will report basically a number back to you. And SO incoming CPU is supported on some NICs, and it will tell you the last CPU core on which the the RxQ was used from, and you should probably try to receive from that CPU core as well. That would be most efficient. There's also, SO incoming NAPI ID, and that's more just telling you directly, this is the number of the RxQ. They're not always exactly one-to-one mapped, but it's more or less the number of the RxQ that this packet arrived on. And what you should do is group all of the connections that share an RxQ together at a minimum. And it's up to the NIC driver to possibly shift the RxQ to be associated with the correct core. Most networking drivers will do that. They'll see that you're receiving from a particular core and move it if they can. Obviously, if you have a lot of sockets that are associated with the same RxQ and they are being received from different cores, then it can't do that. So this is really just enabling us to do the grouping correctly. We group by NAPI ID, and then everything stays together, and the networking driver can realize, oh, 100% of the receives for this RxQ are on this core. I'm going to assign that RxQ to that core instead of wherever it was. That's really on the server side. So there's also an API on the client side, which is brand new and was actually more or less added for SPDK, like at our insistence, where you can do a set sock opt with the SO mark flag, and you can essentially you just give it a number, what your grouping number, and this is a hint to the NIC that all of the sockets that you marked should share an RxQ. The only drawback here is you have to do it before you connect the socket. After you connect it, it's sort of set in stone. It can't be changed. So you can only do this on the initiator because that's where you're able to create a socket, just do this, and then call connect. Whereas on the server, you're just calling accept, and you're getting what you get. So these are the two ways you can align your sockets with the RxQs and avoid kernel locks and message passing and that jitter. SPDK does all of these things as appropriate for the correct NIC, for the NIC that you have already today. Okay, now I want to talk about another subject, which is system calls versus data copies. There's a trade-off to be considered here. So let's talk a little bit about what the code for parsing a storage protocol tends to look like. I'll mostly use examples from NVMe over Fabrics, but iSCSI is similar. So in the most naive sense, you would do a receive on the stream to get the first 64 bytes or whatever size the command is. In NVMe over Fabrics, they're actually variable size. So you would receive the common header of 8 bytes. It would tell you what kind of command it is, and then you would receive the remainder. Most of them are 64 bytes total, or 64 bytes after that first 8 bytes, sorry. And then now you have the command, you would parse the command, and you would say, well, what's this command doing? If they're sending me data, maybe it's an in-capsule write or something, or it's a response to a request for data that I had sent earlier, we would call receive for however much data is to follow the command. Or if it is describing some kind of SGL, maybe that's what's coming in next, and we need to go receive that. And then you repeat. And so you end up doing a lot of receives if you're doing this technically correctly. You're doing like an 8-byte receive on the common header and then a 64-byte receive typically on the command, but there's a lot of conditionals here where things can change sizes or come in different order. So you have to do all these really small receives. But it turns out system calls are expensive. You do not want to be doing a lot of system calls. So how can we avoid this, basically? And so we can realize that system calls have mostly fixed overhead. They're clearing the registers and a bunch of state as the security context of the CPU switches from user to kernel. And that doesn't really matter what you do in the kernel. That overhead is always the same. And we can avoid switching that context by simply trying to receive a bigger part of the stream at one go. And so we just try to receive a large amount into a temporary buffer in user space, and then we parse the stream, this iteration through the stream of look at the header, look at the command, decide if there's data, etc. We can do that all out of the user space buffer instead. The only drawback here is if we find data that we then need to go, transfer to some backend device, write or read, write to a backend device, or we're going to have to copy that out of this temporary scratch buffer that we have into a DMA safe buffer in our buffer pools. And so that copy has an extra cost. So there's a trade-off. And we've measured actually extensively what the cutover point is of how much should we attempt to receive versus how expensive that copy is. And we find that it's typically not even worth calling receive with a data buffer, scratch data buffer smaller than 8K. So the copy is actually fairly efficient because the receive copies into your temporary buffer, which leaves all the data in the cache, and then you're copying out of there. So it's a very fast copy, the second one. And then of course we have all sorts of smarts to know that, like, okay, if the next part of the stream, after we copy our 8K speculatively, we parse through the stream and we start seeing, oh, well, the next 64K is all data, and I've got 4K of it or something from my scratch buffer. So I know the next 60K is just going to be data. Well, I'll receive directly into my data buffers that I've just allocated out of my buffer pool instead of always receiving through the scratch space. But we use the scratch space when we don't know what the next thing is going to be, which is common. So I think that's a really key finding. Everybody who is making a lot of system calls should consider that. It's a relatively straightforward change. All right, and then the third really cool thing I would like to talk about before we get into future-looking things is zero copy transmit. And if we look at what needs to happen inside of the kernel in order to send data, what happens today is you have some data up in your user space application in a buffer. You call send. That copies that data within the system call into an operating system buffer, and then it returns and it tells you, hey, I'm done. It hasn't sent the data yet, but it says, I'm done. I've got a copy of your data. If I need to send it or retransmit it later, I've got a copy. You're good. The kernel then will walk through that data buffer and split this data. It could be large. Maybe say we sent 64K or 128K or something. It'll split it into MTU size packets for networking. Like the default is 1500 bytes. So small, and all those packets need headers and checksums. They need the Ethernet framing, they need the IP framing, they need the TCP framing, and then it will queue those packets up to be sent by the NIC on the wire. And so it turns out the NIC actually can do this splitting and header insertion for us, and that's called TCP Segmentation Offload. The vast majority of NICs available today support this in hardware. And so all you actually have to do with this enabled is just queue up the entire, 64K or 128K, whatever we sent, to the NIC, and the NIC will DMA that down into its internal memory and, split and insert packet headers and checksums as it sends for you. So that's much better. Most NICs are doing that today. And if you notice, all the kernel TCP stack had to do in this path is post the buffer you sent to the NIC. It didn't have to actually do anything, which is great. So this is a required feature to do zero copy transmit, zero copy send, because this is how they've chosen to implement it. If we could, the OS could, when it receives a send system call, tell the application, hey, I've queued up your send, but it's not sent yet. It hasn't been sent on the wire yet, and I haven't gotten a TCP ACK back for it yet from the other side. So please just don't change your data buffers until I tell you it's good. But it leaves the data in user space where it is. If we could do that, then the operating system could just queue up the user's buffers to the NIC and say DMA from here directly without a copy, and go that direction. So that's exactly what Linux has added with a new flag to send called message zero copy. And there is infrastructure to report when the data buffers can actually be released by user space. You actually do a receive message on the socket to read from what's called the error queue, which is just like a sideband message queue that already existed, and it will give you messages saying like, hey, this send call you made that I told you was queued up, it's now done, and you can release your resources. The operating system in this path still must pin the data buffers to make them DMA safe, which has overhead. So this is not entirely free. So it has to like mark all the user space data buffers, as it's pinned so they don't get paged out or moved around, because it's told the NIC about the physical location of these to do DMA, and so they can't move. That pinning is an atomic instruction typically, and it has overhead. But we found zero copy is an improvement as long as you send at least 4K at a time. The official guidance, I think, on the Linux documentation says 10K. We found it's more like 4K, which is perfect for storage. That's the least amount we typically send, unless we're just sending small amounts of responses to other commands. But the smallest amount of data we're ever going to send is 4K anyway. So SPDK elects to always turn on zero copy transmit. There are knobs to turn it off if you're on a platform that, where the pinning is very expensive. But it's almost always a benefit. And of course, at 8K, 16K, 32K, the benefit gets really enormous. So it's a big improvement. So I just wanted to have a little discussion now about why is there no zero copy receive? Uh, and the main issue is the OS drivers have to keep data buffers posted to the NIC so that the NIC has somewhere to dump the incoming Ethernet frames, or the NIC will begin dropping packets, and you don't want it to drop packets and force retransmits. Um, these Ethernet frames are scattered, small, and they're not in order. TCP can arrive in any order, and the software stack has to reassemble the stream from the out of order packets. And then these packets also have headers that have to be parsed and stripped. And the security model of the operating system is to not show the application these headers. They just show you your reassembled stream. So it's actually a much harder problem with the APIs we've discussed so far in this talk. There's some hope where we'll get to that. Um, because we're doing non-blocking receives, or we're doing these receive system calls, and we just provide a buffer to say receive here, but the buffer doesn't stick around in the OS after we've attempted to receive. So there could be periods there where we're not attempting to receive, and packets wind up getting dropped because there's nothing posted at the NIC. So far, this has been mostly an intractable problem, other than a couple of really minor cases. Whereas if you can control the MTU size to be like a multiple of the page size, you can mmap the socket and see the kernel buffers, um, which has some use. It's still reasonably expensive, but if you have ultimate control over your network, that's possibly an option. It's not for SPDK today. So we will come back to this at the very end of the talk. Okay, and now to the future. I want to spend the last bit of the talk on IOU ring, which we see as the future interface of networking. It might even be the current interface. We're kind of in a transition period where it's slowly becoming better than our ePOL based implementation, but it's not 100% there yet. So a little bit about IOU ring. I'm talking to a storage audience who is interested in SPDK. You probably all know about IOU ring, but it's an asynchronous, system call interface on Linux. You basically have a submission queue and a completion queue, like nvme, like SPDK, etc. And you can drop commands into the submission queue, and sometime later you will see completions appear in the completion queue. The equivalent thing of like writing the doorbell after submitting a bunch of commands is a system call. So you can copy a bunch of commands, descriptors is what they call them, into the submission queue of the IOU ring, and then you make a system call to say submit this set. So it gives you great system call batching, which is a major win. It also has a lot of cool features for pre-registering file descriptors, including sockets. With the ring, if you know that you're going to be using the IOU ring from a single thread especially, that will reduce some of the standard overhead the kernel has to do to like validate a file descriptor and to take a reference count on it, etc. So really cool things there to reduce the per operation overhead of the kernel. They have also very recently, in 6.0, I believe, Linux 6.0, added more natural zero copy support. And by that I mean the other zero copy API I outlined was you make the traditional send call, which is used to be like do it or don't, but tell me the result of the send immediately. And they've sort of they sort of found a way to make that asynchronous by saying, okay, I queued up this amount of bytes, and then you have to try to receive on the socket's error queue later to find out when it's done. which is not necessarily intuitive. I think it was a clever way to solve it with the system call interfaces they had. But in IOU ring, they now have like a send zero copy, and it it basically completes when it's done. There's a little bit of complexity there. It does two completions, but it's just sort of a natural async send and tell me when you finish sending it, and it's all zero copy. And so that is really cleaned up. I think it's really nice. Then they also have another mechanism to pre-post a bunch of receive buffers to be used for asynchronous receive operations. I'll talk about that a little bit in a moment. So a little bit about this system call batching. I think this is really promising, and one of the places where we already see big wins using IOU ring. You drop multiple descriptors into a ring. Say you have 1,000 sockets that you're processing on your thread. You can drop 1,000 receives into the IOU ring and then do a single system call to submit all 1,000 of them. And this eliminates the need for ePoll. So um, the only disadvantage here with what I just outlined is that with ePoll, if I have 1,000 sockets, I could allocate a buffer pool of maybe 10 buffers. And I ePoll and I discover which sockets are actually busy, which is necessarily a small subset of the 1,000. And then I do receives into the buffers in my buffer pool, but my buffer pool didn't have 1,000 buffers in it. It was much smaller, and that sort of works out. It's a nice natural flow. It saves a lot of memory. Um, with IOU ring, what I just outlined is you post 1,000 receives, which means I need 1,000 buffers. It takes a lot more memory. Except they have a great way around this, which is you can pre-post buffers to the IOU ring into a pool for receiving. And so I can post my 10 buffers there. And then I can say receive, post my async receive, and I don't give you a buffer there. I just say take one from the pool. And when it completes, it tells you I took this one from the pool. Here's your data. And then you can put it back in the pool when you're done. So that gives you the same sort of memory savings as ePoll. It's great. And another key thing about this is that now the kernel knows about all the buffers you would like to receive into way ahead of when you attempt to make the receive call. And so you have a set of user buffers just sitting around that you've given over to the kernel to say, this is where I'd like to receive to, just waiting. And so there are patches out now, and I don't know if they will be accepted or not, where they use that set of buffers to post to the RxQ directly. They pin them and they post it to the RxQ directly, the RxQs directly of the NIC, and the NIC ends up DMAing there. Now it relies on a couple of key NIC features, namely header splitting. So the NICs often have ways to split off all of the framing from the packets, um, such that they can keep those inside the kernel. And then there's some trickery with what happens if packets arrive out of order. But there is definitely work going on there where there may be a glimmer of hope toward an actual zero copy receive someday soon. Okay, and then I just want to end a little bit on some of the remaining challenges, and then we'll mention a few more things that we're investigating right now. There's a couple of corner case behaviors that are still maturing. Maybe they've fixed them all in 6.1 or something. But a couple of questions on when can you get a partial send. We're doing an asynchronous send. Can it ever complete partially, or does it just not complete until it's done? The answer is it could definitely complete partially. But it's just many fewer cases than before. But what if I put the message wait all flag? And there's sort of all these combinations of things coming together, and it's not 100% clear what they all mean in every case. Those are getting worked out every day. The other one is software needs to be adapted to do all asynchronous socket operations. For SPDK, this is it's a sizable change, but it's not intractable. It sort of fits our programming model. For a lot of other software projects, this may just be impossible. Um, and then, because the zero copy receive is not merged, that's not live right now, and I'm not sure if it's going to make it or not. We still see in benchmarks that the data copy on the receive path, when we're doing receive, is not solved. It's a major performance problem, as it's always been. Um, and then I just wanted to mention a couple other cool things that we're working on right now. They've recently added multi-shot accept and multi-shot receive, which are kind of cool concepts. Basically, you submit one asynchronous operation to the ring, and it will, instead of like if you do an accept asynchronously, instead of every time it finds a new socket to accept, it completes the accept, and then you have to resubmit the accept. It'll just give you a completion saying, here's one socket that I found, but you don't have to resubmit the accept. It just stays out and it just keeps generating completions. You can do similar things with receives, which ties into this pre-posted buffer pool. It'll just keep receiving and picking new buffers from the pool forever. And this avoids the overhead of resubmitting the command. And it doesn't require any round trip time to resubmit the receive. There's always a receive outstanding. So anytime data arrives, it just gets dumped into buffers. So those sort of efforts are ongoing right now in SPDK to try to leverage some of those things, and see where it leaves us with performance. All right. So with that, thank you very much. If you have questions, I'm happy to answer them. And we are always available for more in-depth discussion on Slack.